I work in the group of Professor Mark Robinson Rechavi of University of Lausanne, Switzerland. Can you hear me? Yeah. Yeah. Today I will talk about testing the ortholog conjecture with two different methods using simulated and empirical datasets. Let's see what is ortholog conjecture. For example, vertebrate red blood cells comprise of hemoglobin. This hemoglobin is made up of two subunits, alpha globin and beta globin, which are related to each other by a duplication event that happened long ago in animal evolution. Suppose one is interested in beta globin in human, then what would be the best model to consider? Beta globin in mouse, which is ortholog to beta globin in human, or alpha globin in human, which is paralog to beta globin in human. So as per ortholog conjecture, orthologs are functionally more similar than paralog. If this is true, then we would then it will be useful to consider beta globin in mouse rather than considering alpha globin in human. The debate on ortholog conjecture literally started in 2011, and all the majority of the works supported ortholog conjecture. It still remains controversial even after 7 years. And in the latest publication, Dunn et al. Has shown that one shouldn't use pairwise method while testing ortholog conjecture, as different method can lead to different conclusion. Let's see what are the methods. For demonstration, I have used the same gene trees of 3 fish species. In this tree, you can see we have 7 tips, 6 internal nodes, 2 nodes for duplication, 4 nodes for speciation. So 21 pairwise comparison are possible for this tree, out of which 8 comparison are possible for orthologs and 13 comparison are possible for paralogs. Due to the shared history of the tree, these comparisons are not independent of each other. On the other hand, phylogenetic independent contrast is used to compute contrast for each node. For this tree, we have 6 nodes, 2 nodes for duplication, 4 nodes for speciation. Each contrast are independent of each other, and for this tree, for this node, if we want to calculate the contrast, it can be calculated by this formula, which is actually the difference between the thread value divided by the square root of the total branch length, that is the expected variance. That means higher thread value means higher contrast, higher expected variance means lower contrast. So we asked, what is the best method to test ortholog conjecture? To understand, we considered several models, but due to lack of time, here I'm demonstrating only one model, that is asymmetric acceleration model. It may happen that after duplication, one of the 2 copies, sequence or thread evolutionary rate accelerates for one of the 2 copies. So we simulated gene trees, and we simulated thread along the trees. We used tissue specificity data tau as thread for our study, and we randomly assigned events on this tree. These red points are actually, red nodes are speciation and blue are duplication. Then we gave distinct rates to one of the 2 branches randomly after duplication to create this asymmetric substitution tree. And then we use this substitution tree to time calibrate them based on the speciation time point. At this point, I should mention that in real life, we don't have original time tree in our hand. What we have the substitution tree. And we need to time calibrate them before we apply the phylogenetic method, that is phylogenetic independent contrast. And we also don't know the duplication time point, so we need to use the speciation time point to calibrate them. So here I just want to show that the branch length for the calibrated tree often differs from the original time tree. To execute, we considered two parameters that may change after duplication, that is sequence evolutionary rate and thread evolutionary rate. We considered several hypothetical scenarios, but due to lack of time, I will show the result of 3 hypothetical scenarios. The first one is the scenario where the sequence and thread do not change after duplication. That is the null model. For a good method, null model should work. Here, any change in thread value is actually captured by original time tree. Since the thread rate do not change here, so we do not detect ortholog conjecture in this scenario. In case of, since sequence evolutionary rate also do not change in this scenario, so for these 2 tree, ortholog conjecture is not detected. That means null model is properly working. In case of pairwise method, we can see that the correlation coefficient of tau for orthologs are similar than the correlation coefficient of tau for paralogs. That means null model is working for both the methods. Let's consider a theoretical ortholog conjecture scenario where the thread evolutionary rate after duplication is higher, but the sequence evolutionary rate do not change. Suppose the thread evolutionary rate is 5 times higher after duplication. Since it is 5 times higher after duplication, so the contrast of duplication is 5 times higher than the contrast of speciation, so ortholog conjecture is detected by original time tree. Since the expected variance, that is the sequence evolutionary rate after duplication do not change here, but the thread is 5 times higher, so ortholog conjecture is detected by all the 3 trees. Here in this scenario, we can see that the pairwise method can also detect ortholog conjecture. That means in this scenario, both the method works. Finally, consider one scenario where after duplication, sequence and thread both rates accelerates after duplication, but the sequence evolutionary rate is higher than thread evolutionary rate. Suppose after duplication, thread evolutionary rate is 2 times higher for duplication, but the sequence evolutionary rate is 8 times higher. So in this scenario, the thread is 2 times higher, so the contrast for duplication is 2 times higher than the contrast of speciation. That means the ortholog conjecture is detected by original time tree. But the sequence evolutionary rate is 8 times higher. That means the expected variance for duplication is much higher, which actually creates that the contrast for duplication is 2 by 8, that is 1/4 time of the contrast of speciation. So the ortholog conjecture is not detected by the time calibrated tree in real ortholog conjecture scenario. But even in this scenario, we can see that pairwise method can still detect ortholog conjecture where the phylogenetic method fails. To revalidate our result, we used the time-calibrated trees of 5 fish species, and we considered the time point after third round of whole genome duplication happened. Thereby, we found that both the methods support ortholog conjecture here. But when we use the same time frame, but we use the time-calibrated trees from 16 vertebrate data, we see that the pairwise method can detect ortholog conjecture, but the phylogenetic method fails. From this, we conclude that pairwise method is more robust compared to phylogenetic method in testing ortholog conjecture, and data from fishes, which includes paralog from whole genome duplication, provides support for ortholog conjecture. For more detailed discussion, please come to my poster. Thank you very much for your attention.
Time for a question while we get the next speaker up. Yeah, please.
In your study, so when you claim paralogs, you take them as a whole, but you need to take into consideration there's 3 types of paralogs, right? Have you made any distinction between within species in paralogs and out paralogs?
No, no.
Okay,
We considered all kind of parallels.
Whole,
yeah.
Right? But for instance, if you do comparative evolution between human and mice, they're diverged what, like 15 million years ago? They're gonna have relatively lower amounts of imparalogs, but then when you compare 2 yeast species, that's 400 million years of evolution, right, after speciation, that's going to leave you a lot more within species in parallels. And I suggest if you compare the conservation.
Yeah, we will consider, but for the time being, just we take as a whole.
Okay.
Yeah.
Okay, thank you again. We switch now to Nadia El Mabrouk from University of Montreal in Canada.